This is Stanford Engineering's The Future of Everything, and I'm your host, Russ Altman. If you're enjoying the show or if it's helped you in any way, please consider rating and reviewing to share your thoughts. Your input is extremely valuable and helps others discover what the show is all about. Today, Professor Risa Wechsler from Stanford University will tell us about the universe, cosmology, how galaxies form, how they evolve, and how we're measuring them. It's the future of the universe. Before we get started, another reminder to rate and review the show, particularly if you've learned something new or found it helpful in any way. For thousands of years, we humans have looked up to the skies and wondered about the universe. We see planets and the moon, but we also see stars and galaxies far, far away. We don't really understand the details of how big is the universe. Are we at the center of the universe or are we near the edge? How do you even measure that? Well, Professor Risa Wechsler from Stanford University is a professor of physics, particle physics, and astrophysics, and she is an expert at studying the universe, how it's expanding, and how galaxies within the universe evolve. She's especially interested in the galaxy that we live in, the Milky Way galaxy, my personal favorite galaxy. Risa, you study the universe and the galaxies within the universe. What are the big questions that your group is struggling with these days?
Yeah, so, I got into astrophysics and cosmology because we get to ask and try to answer the biggest questions that we have. So these are questions like, how did the universe evolve from early times until the present day? What is it made of? And how did galaxies form? So big picture, those are the questions that I have been interested in and continue to be interested in. And we have a lot of exciting tools that my group is using to try to answer those questions.
Great. So let's get right into the tools because we could start with a lot of definitions and I'm sure we're going to have to define some terms, but let's just go with, tell us about some of the technologies and what are you measuring and how are you looking at these galaxies and the extent of the universe?
Yeah, that's great. One of the things that I'm really excited about right now at this moment is that we have a bunch of surveys that either have just come online or are about to come online that are going to be able to map the universe substantially better than we have been able to do before. So one of those that we're playing a big role here at Stanford and SLAC is called the Rubin Observatory's Legacy Survey of Space and Time. This is the largest camera that has ever been built. It's a 3.2 gigapixel camera. And we actually just put it in the box last week up at SLAC and are shipping it to Chile very soon. And that camera is exciting because it's going to survey the entire southern sky essentially every 3 nights. Over 10 years, it'll take more than 800 pictures of each patch of the sky with this incredibly precise camera.
Yes.
And that's going to allow us to make a better map than we ever have before. And that's just one of the instruments that we now have or will have in the next few years to make these kinds of maps. So in my group, what we're particularly interested in is essentially how do we use the information from all of these maps, different kinds of resolution, different kinds of data, different fields of view that go to different depths, and put them all together in essentially a self-consistent picture for how the universe evolved, using computer simulations and modeling to try to help us piece together the entire evolution of the universe and what it's made of.
Okay, so great. So that was great because now I have a million questions. First of all, what does a map mean to you? So I think about maps. I think about maybe a 2D map of roads and streets and Google Map. Sometimes you can imagine a 3D map like of the of the solar system with the sun. The planets are going around it. So when you say a map of the universe, is it 3-dimensional coordinates? I'm guessing maybe not, but maybe yes. Tell me what it looks like.
Yeah, that's a perfect question and a perfect introduction to these different kinds of measurements that we can make. So you can think of most of the measurements we make, it's a little bit more complicated than this, but you can think of most of the measurements we make as either a 2D map that can give you some fuzzy information in the third dimension, or a quite precise 3D map. And the way we get, so when you take a picture, you basically have a 2D map. So the way you get that third dimension, which of course we want, because what's super exciting in the universe is when you look far away, you are also looking back in time. So the further away we can look and the more precisely we can pin down what that third dimension is, the better we can really make that third map and go, ideally back to the very early stages of the universe when galaxies first started to form.
And so just to clarify, sorry to interrupt, but the reasons that it's looking back in time is because light takes a certain amount of time to reach us. And so that the things that are farthest away sent their light to us the longest time ago. And so the farthest ones are kind of the oldest. And that's why.
That's exactly right. I mean, we have this wonderful, happy fact of physics that comes from general relativity, that light has a very specific and fast but finite speed. And so even when we look at the sun, that light from the sun is not emitted right now. It was emitted about 8 minutes ago. When we look, when we look very far away, we can start to see light that was emitted more than 13 billion years ago. So that's why when we look far away, we are looking back in time. So in order to get that third dimension, the most common tool that astronomers use is something called spectroscopy. So we essentially have two different kinds of measurements we make. One is basically pictures, imaging, and the other is spectroscopy, where you take maybe a fiber or a slit and you disperse the light as a function of wavelength. So then you get the intensity of light as a function of wavelength. That's what astronomers call a spectrum. And because light that's moving away from you is actually shifted to the red, we measure something that astronomers call a redshift.
This is like the trains, right? This is what we learned in high school. The train that's going away from you gets lower in sound, and the one that's coming towards you has a different change in the sound. And that same thing happens with the lights from the stars.
That's exactly right. From stars or galaxies or quasars. And so that light gets shifted, and then there's some typical features that come from, transitions in elements. Oxygen, for example, has some transitions that, we could even measure in the lab. When we see that at a different wavelength than we see it on Earth, we know that it's moving away from us.
Gotcha.
And one of the projects that I'm involved in is called DESI, the Dark Energy Spectroscopic Instrument. This project has now taken spectra of more than a factor of 20 than all instruments before. So we now have, I think, 40 or 50 million redshifts of galaxies and stars and quasars. And that's a new way to actually make 3D maps and not just 2D maps. So you can't go as deep with that spectroscopy. So we actually do both of these things together and in concert, and we try to put them together so that we can make really deep 2D maps and then also these really nice 3D maps as well.
Great. Okay, so we have a little bit of a sense of how these measurements, and it's great because it's not surprisingly, it's a combination of the images in 2D plus the spectroscopy, and you're getting 3D information. But let's get to the fun part. And I have questions about galaxies, but tell me about the universe. Where are we? So we're in the Milky Way galaxy, if I understand correctly. Are we at the edge of the universe? Are we in the middle of it? And what is the shape? Should I think of it as uniform, just a bunch of points in space, like a fog of clouds, or is it a much more interesting blob of matter? So paint a picture if you can. And I know this is an incredibly unfair question, but welcome to the future of everything.
No, it's a great question. Okay, so the first thing you need to know is that the universe is about 13.8 billion years old. And the other key thing that you need to know about the universe is 13.8 billion years ago, the universe was very hot and very dense and very smooth. And it was definitely smaller than it is today. But we don't have any idea how big it is. And in fact, we don't even know whether it's finite or infinite. So it's a very strange thing, whereas everyone wants to know the answer to your question of where are we in the universe. As far as we know, the universe, whether or not it's finite or infinite, it is way, 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 way bigger than the part of the universe that we can see. So for those purposes, there is no edge, as far as we know. There is no edge. There is no center. We are not at the center, except for that we are at the center of our observable universe, because we are the observer, right? And so we can see in a sphere around us that's 13.8 billion light years away. That's the universe we can see, and we call that the observable universe. That's essentially the edge of how far light could have traveled to us from the beginning of the universe.
But importantly, we do see, no matter what direction we look, do we see stuff? Because that means conceptually we're not, at least conceptually, it seems to me, at an edge. If we can look in every direction and see something.
That's right. And you asked if it was the same in all directions. And the answer to that question is it depends on the scale. So if I look, so on large scales, the answer is yes, incredibly precisely the same in all directions. There is stuff in all directions, and it is essentially the same, actually more than you would even expect. On small scales, it's different. The universe is very, very clumpy on small scales because we had a process in the early universe, which we think actually came from quantum fluctuations, which created little parts where the universe was a tiny bit denser and little parts where the universe was a tiny bit less dense. And most of what has been happening over the last 13.8 billion years is those places that had a little bit of extra stuff to begin with got a lot more stuff now. And so any place that you're in a galaxy is a place that started with a little bit more stuff and eventually collapsed into a galaxy.
Great. Well, let's go to galaxies.
Great.
Tell me about a galaxy. I know you study galaxy formation. You said already that you study galaxy evolution. Talk to me about galaxies.
Yeah. So, okay. Most of the universe is not made of the same stuff that we are or the same stuff that galaxies are, which is mostly stars and gas, mostly hydrogen gas. Most of the universe is actually made of dark matter, and I'm sure we'll get back to that. But what you can think of is that in the early universe, there was dark matter and there was hydrogen and a little bit of helium. Okay. And they were pretty much evenly distributed with a little bit of these tiny fluctuations that were created early on. The key thing that's different between dark matter and normal matter, and I'm getting into dark matter because we actually have to understand dark matter to understand galaxy formation.
And you just talked about a dark matter survey or something a few minutes ago, so clearly it's on your mind.
So we're going to get back to that. So the key difference is that when gas particles hit each other, they cool down. They lose energy. They can emit energy and cool down. That doesn't happen with dark matter as far as we understand. So you have a clump of stuff, which is both dark matter and gas. And eventually the gas particles sink to the center of that clump of stuff. And once they sink to the center, they can start to cool and they can start to form galaxies. This process happens really early on, as we now actually have new images from the James Webb Space Telescope that are further back in time than we've ever seen before. And we know that we're starting to form galaxies already in the first, basically few hundred million years of the universe. So that's when it starts, but it happens in this sort of hierarchical process where you start with only the most dense regions of the universe that can start to form galaxies. And then over time, more and more regions get collapsed enough that they can start to form stars, and they merge together and grow over time, so that every single galaxy, like the Milky Way, comes from the merger of hundreds of smaller things over the last 13 billion years or so.
And it sounds like you've created a typology of galaxies, because in looking through your work, I see mentions of satellite galaxies,
Hmm.
dwarf galaxies, lots of different kinds of galaxies. I don't know if these are ones that you should tell us about, but it's interesting to me because it sounds like that evolution that you just described, that formation and
Yeah.
evolution, can take different paths.
Yeah, well, so the way I think about this is actually fundamentally, I told you in the beginning that what I want to do most of all is put all observations of galaxies into sort of like a unified framework of how we understand how the whole universe formed. So there are lots of experts who think specifically about one type of galaxy or another type of galaxy. That's not me. I like to think about all galaxies at the same time. Although I do have a sweet spot in my heart for these tiny, tiny galaxies that we might talk about later. So galaxies so they form in these clumps of dark matter. The masses of the dark matter clumps that they form in are everywhere from maybe a few 100 million times the mass of the sun, all the way up to 10 to the 15 times the mass of the sun.
Okay, so that's a huge range.
So yeah, like a trillion times, right? So it's like 7 orders of magnitude that you actually are the dark matter clumps that you can form a galaxy. And so because of that, basically because it's a very wide mass scale and the gas processors are different over that mass scale, you get galaxies that look different. You can think of them as forming in different environments. It's like some galaxies you can imagine forming in dense places like cities, and some galaxies, form out in the countryside where there's not a lot of stuff around. Those are the kinds of things that can lead to differences in what galaxies look like. Now, this thing about satellite galaxies is an important piece because what I mentioned is that the way galaxies form is that they start in these initial density peaks and they merge and grow over time. As they merge and grow, it's like the sun rotating or the earth rotating around the sun or even the moon, circling the earth. Galaxies have satellites similar to that. And they kind of come in and they get accreted and they eventually get destroyed and merge into the main thing.
Yes.
But that takes quite a bit of time.
But also, many of the if I'm understanding, many of the principles of gravity apply even at the scale, so that if you have a big galaxy and there's a little one, and if it's close enough, it might, and forgive my language, it might start circulating around that big galaxy in some sense.
That's right. And actually, this is the amazing thing about gravity. I mean, gravity is a theory that we understand incredibly well. It is the only thing that matters on very large scales in the universe. Einstein wrote down a theory, general relativity. It still seems to work on every single scale we have possibly tested it. And that literally means including on the scale of the whole universe. So when I am mostly thinking about how dark matter and galaxies behave in the universe, for me personally, because of the scales that I'm interested in relatively large scales, gravity is the main thing that matters for everything. And we know how it works. It turns out to be hard to calculate because, as you heard, we're calculating things on a very wide range of scales.
Right.
All the way from the details of exactly how the Milky Way formed to how a trillion galaxies formed in the universe. So it's a complicated computational problem, but conceptually, it's just the same gravity that is why you're sitting in your chair.
This is The Future of Everything. We'll have more with Risa Wechsler next. Welcome back to The Future of Everything. I'm your host, Russ Altman, and we're speaking with Professor Risa Wechsler about physics, astrophysics, the edges of the universe, and where galaxies come from. In the next segment, Risa will tell us about dark matter, dark energy, and how she and her colleagues are measuring these things to get a better understanding of how fast the universe is accelerating in its growth. But Risa, one of the things you mentioned that we didn't get into a little bit was dark energy and dark matter. And it sounds like that's quite fundamental. So can you take us through what we need to know about that to appreciate our evolving understanding of the universe?
Yeah. Great. Okay. So the first thing, I am really interested in this basic question, what is the universe made of? Okay. And the first thing you need to know about the answer to that question is that most of the universe is made of different stuff than you and me, right? You and me are made of hydrogen and carbon and oxygen and other things like that. Everything on the periodic table, all of the things that you and me and the sun and the stars are made of.
The entire chemistry AP exam.
All of chemistry AP, and in fact, all of the standard model of particle physics is all less than 5% of what the universe is made of.
Huh.
So we now know that there are these two other things. Dark matter, we think, is matter, but it's matter, so it behaves exactly the same gravitationally as normal matter does, as far as we have seen. And we can see its impact gravitationally on everything from the tiniest galaxies in the universe to how the entire universe as a whole moves and changes over time. But as far as we know, it's a particle, and we don't know what this particle is. So we're looking for it. Wow. We're looking for, it might be really, really small. It might be 10 to the minus 21 times smaller than an electron, or it might be, 1,000 times the mass of the sun. That's a very big mass range. We don't know what it is, and we're looking.
Do we know if it's in our presence, or is it out there somewhere?
No, it's everywhere. It's everywhere, and it doesn't interact with us, so it's probably going through you and me, because we are, the Earth is spinning around the sun, and the sun is spinning around the Milky Way. So we actually are moving through the galaxy as we speak.
Okay.
Through this wind of dark matter. So that's the dark matter. But then there's this other thing that's even stranger, which is not even matter at all. And we call that thing dark energy. It's kind of just a funny name. We don't know what it is. But what we do know is we know how much there is, and we know what it's doing to the universe. So dark energy basically does two things. It changes the way the universe expands over time. And it changes, along with dark matter, they both change how structure grows. So how small things become big.
Huh.
And so we actually, even though we don't know what this thing is, it has an impact on the universe on very, very large scales. And so that's one of the reasons that we're making these very big maps, to figure out what dark energy and dark matter are.
You've described for us a little bit about dark matter, a little bit about dark energy. How do you use these concepts for doing what you really have said now a couple of times you're interested in, which is understanding and mapping the universe?
Yeah, so these maps of the universe are actually really sensitive to both dark matter and dark energy. Dark energy, even though we don't know what it is, impacts things on large scales in the universe. So it impacts how the universe evolves over time. It impacts it in two ways. One is how fast the universe expands, and the other is how fast it gets clumpy. And so by making these maps that I told you about, we're actually separately able to map out how fast is the universe clumping up, how fast is gravity working, and how fast is it speeding apart. It actually turns out the universe is not just expanding, it's actually accelerating. And that is the key reason that we know that dark energy is a thing. It's probably like a property of the vacuum itself that kind of pushes one bit of space away from another bit of space. So we know it's accelerating. We don't know why. And we want to measure how fast as well as we possibly can. So that's dark energy. Now, dark matter it does impact how fast the universe expands and how fast it gets clumpy. But it also, because it's probably a small thing, can do all kinds of other things. We want to actually understand what's the mass of the dark matter particle and also how it interacts. And we have lots of ways to do that. Actually, some of my colleagues here at Stanford and SLAC are trying to build experiments deep underground to try to catch dark matter in the act and see if it actually interacts with us. What I'm personally doing is trying to understand how dark matter behaves on the scale both of the whole universe and on the scale of individual galaxies, because it turns out that what dark matter is, like actually what particle it is, can influence things like how many galaxies there are, how clumpy they are, how they behave, how they move. And so one of the ways I've been thinking about that recently is there's another kind of map we make, which is actually a very precise map of the Milky Way itself. And there are some things that we can only measure in the Milky Way, including the tiniest galaxies in the universe, which these small ones are like only a few hundred stars. And the way they move actually is very sensitive to what the dark matter particle is. So that's a new tool we have to learn about what that is.
Great. So now you had mentioned this saga survey,
Yeah.
and you had so much excitement that I want to make sure I ask you about it and why we all need to be excited about it.
Yeah. So, big picture, we live in the Milky Way. And I already mentioned to you that there's many things that we can only measure at high precision in the Milky Way. But of course, the Milky Way is one galaxy, and it's one of probably a trillion galaxies in the universe. So every time we measure one thing really precisely, we always want to know, how does it fit in? How does it fit into everything else we know? So actually, about 15 years ago, a colleague of mine, Marla Jiha at Yale, we were very frustrated by how often it was that people were comparing models of all the galaxies that look like the Milky Way with this one galaxy, the Milky Way. So we thought, okay, well, let's find 100 of them. And that was a kind of ambitious plan at the time. The thing we were interested in specifically is, we'd like to know everything about these 100 galaxies that are similar to the Milky Way. What we specifically targeted was their satellite galaxies, their bright satellite galaxies. In the Milky Way, we actually know right now of almost 60 galaxies that are orbiting our own galaxy, but some of them are so tiny that you can only see them even very nearby. You can't even see them at the edge of the Milky Way.
Wow.
So here, what we wanted to do was find the satellite galaxies around these 100 Milky Way-like systems. So it was quite an ambitious project, both theoretically and observationally. But we found we have these 100 systems now, actually 101, and we have identified almost 400 satellites that orbit these 100 systems. And so what that does is it helps us understand the context of our home. Everything we measure about the Milky Way, we can now put into context with these 100 other systems to understand, how it varies as a function of their formation history.
Right. So it's just like, I'm a doctor, I sometimes get involved in clinical research, and you can give a drug to one patient and it'll work or it won't work, but you have no idea if it's actually going to work for everybody else. But if you give me 99 other patients, then I begin to have some idea of what's a normal response and what's abnormal. So it's kind of easy for me to believe that by looking at 100, and I'm interested in this idea, you must have had to define what similar meant.
In this case, we actually just looked at mostly basically how massive it was, right? And I can take your analogy a little bit further, right? If these 100 people, they have different genetics, right? Their parents may have been more or less likely to have had heart disease.
Absolutely.
And same thing with these 100 Milky Ways. They have had different formation histories. They were formed in different environments. Some of them essentially were formed in cities, and some were formed in the country. Some of them actually, had a progenitor which was very massive 10 billion years ago, and some of them actually just kind of caught up very late. So that's the kind of diversity that we can try to understand and put the Milky Way into context.
So I take it that when you make these measurements, you're seeing the fingerprints of their history in the measurements.
Exactly. That's exactly right. And that helps us understand the Milky Way much better. We now know a ton about the Milky Way, and it's a really exciting time because we're able to map it much more precisely with the next generation of instruments. And hopefully learn more, not only about galaxy formation, but also about dark matter. We sort of know the Milky Way formed a little bit early, but then it had this interesting collision that happened only 1 or 2 billion years ago with an object called the Large Magellanic Cloud that was pretty massive and brought in a bunch of its own systems with it. And so that turns out to be a really important thing for understanding all of the details that we can only measure in our own system.
I just have to ask this question. When I was a kid, I had a telescope. I looked at the stars, and the only other galaxy I was ever sure that I saw was the Andromeda galaxy. Is that one of the 100 others?
No, and there's a reason it's not. It's so close that we actually can't see most of the whole region around Andromeda. So we actually have to go far enough away that we can see the whole system.
Fascinating. Well, thanks to Risa Wechsler, that was the future of the universe. Thanks for tuning into this episode. With over 250 episodes in our archives, you have instant access to a vast array of discussions on a variety of topics that tell you the future of everything. If you're enjoying the show, please remember to consider sharing it with friends, family, and colleagues. Personal recommendations are one of the best ways for the show to grow. You can follow me at Twitter or X at RB Altman, and you can follow Stanford Engineering at Stanford ENG.